Flattening a design removes the hierarchical structure between modules, and the design is converted to the equivalent of having coded everything in one module. Flattening is used by the simulation program to make the simulation run faster. In our example, the test bench is at the top of the hierarchy, and hence our test bench is the top level module, and it's not used by any other module. The test bench with the instantiated module illustrates a simple hierarchical structure where we define the design in one module and then use it in the test bench. When the Verilog simulator simulates the test bench, it undoes this hierarchy to produce what's called a flattened representation. The hierarchical approach is good for us as humans to manage complex and large designs, but the simulation software handles the simulation in a very efficient way by flattening the design. All signals are visible at the same level, and it's the same as if we coded everything inside one big module. The module instantiation, shown here, is replaced with the actual module contents for the AND/OR, and the connections are made to the ports. When the simulator is used with this test bench, it produces an output that can be viewed in a waveform viewer. You can see some of the signals here, for example, in 1, in 2, in 3, and out 1, referring to our in 1, in 2, in 3, and out 1 in our test bench. You'll note that we also have A, B, C, and G, and these can be seen in our waveform viewer also. However, because in 1 is connected to A, they both have the same value. And you can see that with our waveform. If you take in 1 and trace through the actual waveform, it's the same as A. And that's because they represent the same values. Let's take one time instance and see the values on the inputs and output. So the time instant we take is the one highlighted with the yellow line here at 24 picoseconds. You can see we've the value 1 on in 1. So in 1 contains 1. We've the value 0 on in 2. And the value 0 on in 3. And with these three values supplied as the inputs to the AND/OR instance, you'll see that the output resulting from that is 0. And that's just one set of inputs. You can check other input values and see that the output is correct by examining this waveform. In addition to viewing the simulation output as a waveform, the code in the test bench generates a text output, which looks like this. The highlighted code shown here is responsible for generating this output, and in the coming segments we will see the details of how to produce this type of output. You can see that the strobe task uses format specifiers, %b in our example, where %b indicates that the output will be in a binary format. More sophisticated test bench code can be used to automatically produce a pass-fail result when the test bench is simulated, but is typical for larger designs. The test benches we use in this module will be relatively simple and typically produce waveforms or textual output in table format, such as the one shown here. And using the waveform or the table output, it's up to you, the designer, to determine whether the output is correct or not. From your previous digital course, you will have encountered the binary number representation, consisting of the bit values 1 and 0, and these two values are allowable values for signals in Verilog. 1 is a logic 1 or true condition, and 0 is a logic 0 or false condition, and the two provide us with the 2-bit values that we encounter in binary. Long before the Verilog language was developed, early logic simulators added 2 additional values that help with debugging logic designs. In the 1970s, the Z value and X value were introduced. The Z value is used to indicate a disconnected condition. The equivalent physical manifestation of the Z value is a high impedance output encountered with tri-state logic, or floating when no connection is made to an input. So for example, the output of our tri-state logic gate here is a high impedance output, effectively indicating that there's nothing driving the output, and we can indicate that with our said state. In a similar way, if you have a wire with nothing driving it, it can be denoted using the said state. So said indicates a floating state. This proves useful when debugging, and on occasions you will see a signal with a value said, most likely indicating that it is not connected to anything. This could occur if a port has accidentally had a connection omitted. It's denoted using either upper or lowercase said. X is an unknown logic value. It occurs in instances where the result of an expression or the output of a gate cannot be determined. For example, if two different logic bit values are used to drive a value on a wire. This is shown in this example here, where we have a buffer with an input 0, so the output will be 0. We have another buffer here with the input high, so the output will be high. So you've got a high and a low connected together, and the result of that is to produce an unknown value indicated by X. Another example of where we can encounter an unknown value is in this case here, where we've got an AND gate. One input is connected to a high, indicated by the 1 value here, and the other input is floating, indicated by the said value. In this situation, the output of the gate is unknown, because for the gate to have a value 1, we'd need both inputs to be a 1. For it to have a value 0, we need at least one input to be a 0. And in this case, we don't have either of those. The X value is great when debugging, particularly with sequential logic, and it's denoted using either upper or lowercase x. Verilog supports 4 basic values that a signal can take: 0, 1, x, or said, and this is known as the 4-value set. Most of the predefined data types in Verilog use this value set. If we go back to our simulation output slide, you'll notice that we have a red line in the middle between a high and a low, and the red line in this position indicates an X value. And for the case of said values, it's shown on our waveform using a blue line. Here we have a very simple gate. It's a 2-input NAND gate, and the truth table for the gate looks like this. For example, if you take the value 0 on the B input and the value 1 on the A input, the intersection of the row and column gives us the output. So for this example, we have a 0 on B and a 1 on A, the output is 1. Now we've just seen with Verilog, in addition to the 0 and 1 values, we also have the X and Z values. So now we need to see the truth table accounting for these additional values. In the case of B equal to 0, if we take A equal to X, the output will be a 1. Since the NAND gate produces a 1 output when either input is a 0 or both inputs are 0. In other words, because B is 0, the value of A does not alter the result, i.e. a 1 on the output. If we now look at this column in which we have a said on the input A, we now have an output of 1 for the same reasoning that one of the inputs contains a 0. And you can see that this means we have a 1 here and here. Next, if we look at the case of 1 on the input B and X on the input A. In the case of B equal to 1 and A equal to X, the output now depends on X, and we cannot say whether the output is a 1 or 0, as it depends on X being a 0 or 1. So our output is labeled X. In the case of B equal to 1 and A equal to Z, it means our input is floating for the input A. We cannot determine whether the output is a 1 or 0, so the output is an X in this case also. and that means we have an X here and here. If you continue to fill in the table, you'll find that you have X in these other entries. The truth table for the other logic gates are shown here. Take a look at these entries and see that you are happy with the actual values given. This slide shows the truth table for a NOT gate. The NOT gate is our inverter that looks like this. It's a single input, single output. And you can see that if you've got an X on the input, you have an X on the output. The following is a nice example to illustrate the 4-value set. If the input to the simple circuit is an X, what is the output? So we've got an X on the input here, and the question is, what's the value on the output? The circuit consists of an inverter and a 2-input OR gate. Take a minute or so to determine the output. To determine the output, we note that when we have an input X to the inverter, the output is X. This leaves us with an X on both inputs to the OR gate, producing an X on the output. So our final answer is X, indicating the output is an unknown value. Let's look at an incorrect approach to address this problem. We have an input X here, meaning we have an input X on this input to the OR gate. The input to the inverter is an X, and you may be tempted to say that the output of the inverter is X bar, leaving us with X bar and X as the inputs to the OR gate. And this may lead you to think that the output must be a 1 on the OR gate output. The problem with this analysis is that our value set in Verilog only allows us to have a 0, 1 XOR set. There is no such thing as an X bar value. So our analysis in this approach is invalid. So when working through designs using our 4-value set, remember these are the only 4 values that you can have. If we go back to our correct analysis, you'll note that we ended up with an X on the output here. One additional point to note is that when we have an X on both inputs to a gate, this does not mean that we have the same unknown value on both inputs. So you can't assume that this represents 0, 0 or 1, 1. So you cannot take it that an X here and here indicates that you've got the same value here and here. There are 2 groupings for data types in Verilog, the net group and the variable group. The only type in the net group that's of interest to us is the wire type. Wire is a keyword in the language. In the variable group, the most important type for our work is the reg type, but we will encounter the other types such as time and integer later in the course. Reg is also a keyword in the language. So for the moment, our focus will be on the most important types, the wire type and the reg type. We sometimes use the word signal as a general term to refer to nits or variables in our designs. The word signal is not part of the Verilog language. Let's look at the reg type. Reg is in the variable group for data types, and all variables have storage. This means that we can view a variable of type reg as a space in memory in which a value can be held, and that value is identified by the name given to that variable. The value stored in one can be changed, and for the reg type, this can only occur using a procedural assignment. For the moment, the best way to think of what a procedural assignment is an assignment that occurs inside and always or an initial construct. The reg type allows a specified number of bits for storage and the default is 1. What this means is that if in1 is declared to be of type reg, in1 can store a single bit, which means it can take on one of the 4 values from our 4-value set. The reg type can be used in test benches and design modules, but for the first few weeks we will only use the reg type inside a test bench. This simplifies the coding of our design modules. And for the first 3 labs, you should only use the reg type inside the test bench. Here is a declaration whereby we declare in1 and in2 to be of type reg. This has the effect of creating 2 storage spaces, one labeled in1 and one labeled in2, and each can store a single bit. To assign a value to a reg variable, we do so inside an initial construct. And once a value has been assigned, that value is held until a new value is assigned to the reg variable. A very important point to note when starting with the Verilog language is that the reg variable is not equivalent to a digital storage element such as a flip-flop or a latch. This is an unfortunate feature of the language, that the reg keyword might indicate that it's actually a way in which to model a digital storage element such as a flip-flop. When starting with Verilog, the important point to note is that a reg variable is used to store a value that's used during simulation. The other important type that we want to deal with is the wire type. Unlike the reg type, a wire type does not allow us to store a value, but instead has a value based on what is driving it. It's used in test benches and design modules. And a good way to think about a wire in Verilog is to consider it as a physical wire in a real circuit. This now makes it easier for us to understand what we mean when we say a wire type does not store a value, but instead has a value based on what's driving it. It's only when something is driving it does it actually have a value. And that's the same idea in Verilog. It's only when we drive a value onto the wire does the wire actually hold a value. The first example shown here is when we instantiate a module. Let's take our AND/OR module, and we make a connection to the output G as part of our instantiation of the module. So what we're doing is we're connecting out1, which is declared to be of type wire. So out1 is a wire, and we make a connection to G. And what this means now is that out1 is connected to G, so whatever value G has, out1 will have. So in other words, G is driving a value onto out1. This is a very common use for a wire in Verilog, and you can think of out1 as our physical wire. A second example is the use of a wire in an assign statement. In Verilog, when you use an assign statement, we drive a value onto a wire. So W2 is declared to be of type wire, and by using it on the left hand side of the equal to in an assign statement, we're driving a value onto the wire, and the value we're driving is determined by the value of the expression on the right hand side. So in this example, A, B and C are signals that are used as part of the expression, and the value of the expression provides a driver for the wire. So W2 will hold the value produced by the expression. And again, you can think of W2 as our physical wire. To summarize, our approach for the coming weeks is that we will focus on combinational logic in our design modules. We'll only see wires inside the design modules, and later on, after week 4, we'll consider the use of the reg type in design modules. But for the first 4 weeks, design modules will only contain wires. For our test benches for the coming weeks, we will use both the reg type and the wire type inside test benches.